Hello class, today I want to have a discussion about our favorite topic, which is chemical potential, fugacity, and fugacity calculations. Fugacity and their calculations. First of all, let's try to recall together why we end up with doing this. So the reason is we are moving from when one thinks about the system that is composed of multiple components, multiple phases, then I hope you realize that we have to take a look at our previous energy equations. We have to re-evaluate the energy equations, which is internal energy, Helmholtz, H and G, right? So for example, for the Gibbs energy, now G is the Gibbs energy of the whole system is a function of both the temperature, pressure, and the composition, right? So following this discussion, then we would have our interested quantity, which is the full derivative dg is a partial derivative of g with respect to t while keeping p components fixed dt plus partial derivative of g with respect to p while keeping temperature and components fixed dp plus dg over dmi. Then of course I need to have a summation because I'm going to do this for all the components. So I need a summation. I goes from 1 to m. M is the total number of components. There I would have dg over dmi while keeping temperature, pressure, and other components fixed. So this is when we realize that, hey, now from the previous discussions, we understand that if this is still for the one component, multiple phases, those relatively simple systems, then I would have this dg dg over dt. This is still negative s dt. Then I would still have this as v dp, but the following term is slightly complicated, involving a new partial derivative. So this is why we call this as mu. I'm actually missing. First thing is dmi. Then I'm going to define the whole partial derivative as mu I. So now we're going to have summation of I equals 1 to n. That is mu I dmi. Okay, so now you see that I'm going to have this still as my dg for complicated system involving multiple components and multiple phases, then this is my new equation to this Gibbs energy. And I hope you still recall that in general I'm going to use all those terms, the negative S dt v dp, and then mu I dmi. Okay, so if you still recall the equilibrium criteria, whether this is a simple system or a complicated system like we are discussing here, multiple components, multiple phases, always we are interested in target of interest. Let's call this as target of interest is always equilibrium. Okay, where I'm going to see what if I'm using there, I'm going to see if using energy which is U, H, A, and G as a descriptor for the equilibrium. I would expect I'm going to have energy decrease, and they would remain. This is U, H, A, or G. Then over here I would say, hey, this is not changing, so there I'm going to have equilibrium. This is the first choice we could have. The other is if using entropy as a descriptor of the system status, whether it's at equilibrium or not, then we understand from the previous discussion that we would expect entropy will be increasing till not changing. This is again equilibrium. Okay, that is the other message we discussed in class. And then the very next thing is we try to discuss. Now let's try to take a look at a system. We say I have the general information and I have the tools. Then we want to take a look at what is going on. That I'm having a system of alpha and beta. Okay, could it be liquid vapor? Could it be liquid solid? Could it be solid and vapor? So I'm having two systems, and we said this is at equilibrium. It's not changing. It's not exchanging energy or components with other phases. So this is why we have the discussion carried out. We said let's say now let's consider what? Consider we are having a container at equilibrium. While it's at equilibrium, then we are not going to have any exchange of energy or components. So there we have to satisfy this is closed, this is rigid, this is what? Insulated. Okay, so by doing the three, we are going to see if this is closed, then what? I'm going to have dmi is 0. no molecules can move in or out of the whole container. But of course, they are able to move between the two phases, alpha and beta. It is also rigid, meaning the volume, total volume, is not changing. Otherwise, if the volume itself is changing, then we are going to make temperature or pressure, and then different molecules at slightly different distances will have a different increase or decrease of the molecular interactions. So there you are going to induce a new driving force. So we need to satisfy this dV is 0. Isolated implies that there is no energy change at all. So the total internal energy of the whole system, meaning the alpha and the beta phase, their total internal energy would be 0. On top of that, if you recall during the class, there we use the criteria of the total entropy of the alpha and beta phase. We say now at equilibrium and we satisfy dS, which is the change of entropy for the alpha phase plus the change of the beta phase, should be 0. This is because it's at equilibrium already. So I hope you can review some slides we discussed on lecture 13. So now following the discussions and the slides of lecture, I believe this is lecture 13, then we are going to have 3 criteria, which is T alpha, yes, T beta, P alpha, yes, P beta, mu I alpha, yes, mu I beta. So there, of course, we have to satisfy all the components from 1, 2, 3 all the way till component N. They have to satisfy, each component would have the same chemical potential in the two phases. But of course, mu I in the alpha, we don't have to satisfy mu J in the alpha. So that is okay. But the component itself, the chemical potential should be exactly the same throughout the container, that alpha and the beta phases. Okay, so this is almost the discussion we had for the chemical potential. But of course, we need to have that understanding that chemical potential is derived by the 4 energy equations. So there, the interesting, also important thing is definition of chemical potential. Which is mu I can use the internal energy du over dmi. If that is the case, recall the four derivative energy equations. This is SV and prime. If I'm using this as enthalpy dH over dmi, that shall satisfy S, pressure, and prime, which is same as dA Helmholtz energy dmi. There I need to satisfy T and volume m prime will be fixed dg over dmi. This is Tp m prime. Alright, this is the first definition. And then for this mu I, when this is defined through the Gibbs energy dg over dmi, Tp m prime, because of the fixed compositions, the fixed parameters agree with the same definition of partial molar property. So there we call this as Gi partial. This is partial molar property. Partial molar Gibbs energy. Okay? This is my definition of chemical potential. Alright. Then the other thing we discussed would be the let's call this part A. This is A. Try to revisit the chemical potential. Part B is the use of chemical potential. Mu I. We define something and we tend to use it. So if you recall, we derived a quite useful equation, which is now this mu I is partial molar Gibbs energy, which is also a state function. Mu I state property. By state property, we have this mu I is a function of T, P, and N composition. This is why we are trying to somehow double check the d mu I over dt, d mu I over dp, and d mu I over dni. Right? To see what would be the surprises out of these three partial derivatives. So there we received a quite useful equation by looking at this. There we figured out and we proved by switching the order of derivatives, we realize this is Vi, partial molar volume. This is partial molar volume. Okay. So along that discussion, we now we have figured out a quite useful equation. Then we try to use it. So the further use of the chemical potential is along this equation. And what we have is now if we apply this, we call this as equation 1. To ideal gas. Then we have this now this is ideal gas. at a fixed temperature is RT over Pi. We move this, we try to reorganize this a little bit, then we figure this is d mu I. But of course this is still for the ideal gas at a fixed temperature. This is RT d log Pi. That is ideal gas. And fixed temperature. We call this as equation 2. So after that equation, then we have thought about two things. One is this is the for derivatives. Then if I'm going to run this integration, then I would have for to calculate the chemical potential change between two states. Then we simply integrate this as initial to my final d mu I will be RT d log Pi. This is my initial and final. We discussed, and I want to emphasize here that for the initial, the choices of initial states, or we sometimes call this as reference. Then usually we choose one is standard state, one is ideal gas state. So for this, the standard state P shall be 180, right? For the ideal gas state P, let's try to use this as general initial. Should be to 0 or as low as possible. How about the temperature? Temperature, we don't specify the temperature values in order to pick up the initial states, but you can see that the equation so far we are talking about is always at fixed temperature. So we are not changing temperature for the chemical potential calculations. So usually the T initial is same as T final. Same here, T initial is T final. Temperature is a fixed value. This is 1. The other is as Louis, he realized that we have to satisfy the ideal gas assumption. So what about real gases? Then of course I don't have that equation 2, but in order to make use of that idea he defined, now we have the second use of the equation 2 is to define. One is nice discussion, the other is to define fugacity, which is effective partial pressure. So now by looking at the equation 2, we write down d mu I at that same temperature, but this is real. Gases shall be RT d log Fi. Okay. Condition is real gas for fixed temperature processes. This is equation 3. Okay. Then of course we can do the same to run the integration and so on. The small note here is when the pressure goes 0, we are moving from the real gas to the ideal gas, and this is Pi. Okay, and Pi over there can further write down this Yi times P total. Okay, so we are very happy. We are very happy to have an equation for real gases. Oh, then of course the question is, well, what would be the deviation? What would be that difference? So, natural question we would have is when you compare ideal gas and real gas, you want to understand how far away one is from the other. So we can always compare as long as we have two states. The compare could be between ideal gas and real gas, or real gas with the initial state or the reference. So this is why we also defined a few coefficients. Then in order to answer those questions, we define some coefficients. So the first one is phi I, which is the fugacity. Coefficient. Defined by Fi versus Pi. Okay. Of course, Pi is Yi times P total. Second is what is the second? The second is the activity. Right. So we also need to understand activity, CT. Activity is we use AI, which is defined as the difference between Fi and that standard state you picked up. The third is so-called activity coefficient. Gamma I is defined as AI over Xi. AI is of course Fi xi times Fi naught. Okay. And as we discussed, this is always quite nice to correlate the vapor with respect to the liquid at equilibrium. Okay. So we could probably understand this as mainly for the vapor, useful for the vapor. This is quite useful to include the liquid phase. Right. Now here I want to mention that we discussed later on when we were talking about the Fugacity calculations this Wednesday. We know the general equation is always Fi for the vapor phase would be always the same as Fi. The liquid phase would be always in the vapor phase. That is always a valid equation to start with. And then you can see that if I'm using fugacity coefficient and activity coefficient, I can convert that as what? Fi of the vapor will be phi I, yi over the pressure. Fi of the liquid will be what? Gamma I, xi, Fi naught, right? So when we are using that tool, then we could have phi naught. This is also a general equation. We don't specify anything about dilute, anything about low pressure, anything about real gas. So this is a general equation and very useful equation as well. Let's call this as equation 4. Right. So this is how we discussed our calculations for the fugacity. Now we defined a new quantity from the chemical potential to fugacity. Then of course we want to apply that fugacity concept to a few different systems. So this is B. Then as a product of chemical potential application, we define the fugacity. So now we try to take a look at what that fugacity is. C is fugacity calculations. The importance of the fugacity calculation is from we start with the equilibrium. Say this is equilibrium. Criteria or descriptor. We start with this T alpha, T beta, P alpha, P beta, Gi alpha, moving from T alpha, T beta, P alpha, P beta, chemical potential alpha phase, same as a beta phase. We also prove this is equivalent to P alpha, P beta, Fi alpha, Fi beta. So this is why we want to measure temperature and pressure. We want to measure or calculate fugacity, so that we are able to say something of the system, whether it's already at equilibrium or not yet. So for the fugacity calculations, then we start with ideal gas, right? So we have it defined, then we try to look at into gas. For gas, I hope you recall we discussed the following cases. One is this is ideal gas, which is straightforward. Fi will be Pi will be Yi P. Right. The second is it's not ideal gas, but molecules are similar to each other. Their interactions are close to each other, because this is ideal solution or ideal mixture. Then we say this Fi will it be Yi Fi pure. Okay. And this is called general Raoult's law. LUL. Or this is Louis Randall. This is another useful equation. Equation 5. Okay. Using this general Raoult's law, we further derive that at low pressure we would actually have this fugacity of the pure liquid is very close to the saturation pressure. Okay. Then if this is the case, then we could have then we would have for gas it's Fi is Yi P. This is for the vapor. For the liquid, Fi of the liquid is Xi Fi pure, which is Xi Pi set. Therefore, we will have from FIV is always FIL. We have YIP. Okay. That equation is very useful. This is equation. Let's call this equation 6. And this is the so-called low pressure form of Raoult's law. The assumption is this is ideal mixture or solution at low pressure. Alright, so this is for the two cases so far. Then the third case we discussed is I'm going to have dilute component 2 in solvent 1. Okay. If this is the case, I hope you recall that we had the discussion. We are using Taylor series expansion, and we try to pick up. This is at x2 goes 0, and of course corresponding f2 is 0. And we use Taylor series expansion to expand at that equation, which is f2 now is described at f2 at x2 goes 0 plus df2 dx2 tp fixed x2 goes 0 times x2 minus 0. Okay. No, I also need to have half. No, this is the first. Don't. Second would be half tp x2 goes 0 times x2 minus 0. Following would be the higher order. So this is simplified. Now this term is 0, and all those would be the higher orders. We don't tend to include, so this would further reduce that into partial derivative Fugacity of component 2 dx2 at fixed temperature pressure x2 goes 0 times x2. So now if we call this as h2, then we would have this as x2 h2. Okay, this is the Henry's constant. So this is f2. Excuse me. Of course, we need to satisfy this. Is x2 goes 0, then we excuse me, have this equation. What's the number? This is equation 7. Another very useful quantity from the composition and Henry's constant. Like we discussed in lecture, it is quite important to keep that in mind. Is H2 is indeed a function of temperature, pressure, component. So if I have two components, one is the dilute, the other is the solvent, then this is at least depending on the solvent itself. So I have this M prime. Okay. This is the easy and very interesting special cases for the gas part. But if we cannot do anything, cannot simplify anything, then we understand we have to do the calculation. So we are using TPX, we are using TVX, and I'm using Fugacity coefficient phi I, which is defined by phi IP for the calculation. Right. And I hope you somehow recall that. Now we can try to use the equation of state. We can use the variable equation of state. I can use corresponding state theory, all those terms for that calculation. This is a little bit complicated, but I hope that if we provide the equations, then you should be able to finish those calculations. This is for the gas. And how about for the vapor? No, for the liquid. Liquid. Right. For the liquid, we try to have a discussion as the following. One is Fi of the liquid is Fi of the vapor. And then calculate the fugacity of the vapor. Right? If we are able to identify a proper equation of state and calculate the fugacity of the vapor, then the liquid fugacity at equilibrium will be there, exactly the same value. The second we have is the general discussion of high pressure non-saturation cases. So there we have to think about the pressure effect and what would it be the pressure increase will result in the fugacity change to the liquid phase. So I hope you still somehow recall that we are using the two equations. One is d mu I over dP at fixed temperature. Composition is Vi partial. So this is the equation we introduced before, which is let's take a look at if we have a name for this. This is equation 1. This is equation 1. The other is d mu I is RT d log Fi, which is the definition of the fugacity, and that is the equation 2. Combine that two equation, we can have d log Fi over dP, replacing this d mu I at that fixed temperature, and composition would be Vi partial molar volume over RT. So now we cannot assume we are going to use the saturation pressure as the fugacity of the liquid. Then we have to run the integration. So on the initial state, we call this as fugacity at that saturation pressure. This is the liquid fugacity of the high pressure, d log Fi. On the right hand side, we are going to have P saturation. So here is Fi set, yes, P set at low pressures. So there I'm going to have a P set, and this is a high pressure. Okay. Then I'm going to have Vi of the liquid phase, partial molar volume of the liquid component I of RT dP. So if we solve for this, then we have this Fi of my interested high pressure will be Fi of my saturation. Okay, exp this term. Have not evaluated that yet, so put everything all together. And I call this as a correction because it's too complicated. Don't want to calculate, so we just call this as Pauling correction. Alright, so this is other equation for a general liquid phase. You have no access to vapor, you only have liquid solid equilibrium, and the pressure is really huge, so you want to run exact calculation. This is the way to go. So this is equation 8. Right. Solids. For solids, usually we don't we're not that interested in solids for the following reason. See, because fugacity is partial, effective partial. Pressure, or the tendency of escaping from phase A alpha to phase beta. So now if you try to check on the physical meaning of fugacity, you feel like, hey, for a solid, I'm not going to lose too many atoms from the solid phase into a liquid phase or into this vapor phase. So this is why, in general, the discussion of solid fugacity is not too interesting. So we tend to go happily with the gas fugacity calculations and if needed, we try to look at the liquid fugacity calculations. Okay, so this is the short, it's actually not quite short, it's the review for the chemical potential, fugacity, and their calculations. But now I want to discuss some examples. So I want to discuss the part D. Would it be examples of chemical potential and fugacity calculations. Okay, so I want to discuss the this is indeed the examples of lecture 16. Okay, so the first example I want to go over together with you is say this is example 1. No, let's talk about this. So in general, when you know the temperature, so in general we know Tp and N. If I have that information, then I could calculate or correlate this mu I is defined as dg or dmi Tp m prime. This is one very useful equation. From there we call this as partial molar Gibbs energy, which is okay. So there I can take advantage of the Gibbs energy definition. The other useful equation is of course the definition of fugacity, which is d mu I at that fixed temperature is RT d log Fi. So there is a connection of chemical potential, Gibbs energy, enthalpy, entropy, fugacity, and then of course the fugacity is related with Fi yip. Okay, now you can see that it is related with fugacity coefficient, and then of course the pressure is here, right? And the other general equation, as I mentioned, would be Fi in the liquid is always Fi in the vapor. Sometimes I use G, sometimes I use V. So those would be very useful equations, concept. Okay. So let's take a look at the example 1. Example 1. Let me try to find this file. Problem statement. This is the first example. Okay. So this example is let me see where I got this example. This is problem 3, midterm 2 of 2017. So let's take a look at this example. So the idea is use the data from steam table, calculate the fugacity and fugacity coefficient for saturated steam at 1 atm basically. Now the keyword is saturated steam, right? So by doing this, we know, if I know the P is 101 kPa, by using the saturated steam table, this is saturated steam, I shall know the corresponding T. This is number 1. Number 2 is let's try to go ahead and get the value. And I'm looking at the solution I have, and I believe from the steam table, this is 100 degrees C, right? 180 and 100 degrees C sounds correct. And the corresponding value would be H. For the vapor of the steam is kilojoule per kilogram. Of course, the corresponding entropy of the vapor phase is kilojoule per kilogram Kelvin. So now we with that information, we want to start our calculation. And the idea is this is the equilibrium. We are going to have a vapor, we have liquid. But I just need to calculate one for the fugacity because they are exactly the same. So if we stick with this vapor, then I'm going to try to see this equation. Definition is dg over dmi. We discussed is T Pm prime. And then, as I mentioned, we always use this energy definition, H minus Ts as a 1. And then the other is d mu I. The definition of fugacity is RT d log Fi. Keep that in mind that the temperature is not changing. This is a fixed value. So in order to evaluate the current, then I'd better pick up a reference. So this is why we go from this equation to mu I for my interest Tp minus mu I of a reference is RT log Fi of my interest Tp of Fi for my reference. Okay. So I want to calculate this. What is this value? So in order to calculate that, I need to pick up this is the core part, need a reference. Okay, and I want to use that reference. I want to pick up a reference at the same temperature, which is 100 degrees C. But the pressure, I want to use this as for the pressure. I want to use a low pressure, P goes 0, so that I don't need to calculate this calculate Fi naught, but use the ideal gas behavior. Fi naught, if this is ideal gas, would it be what? Would it be Pi? Right? So this is why in the calculation we pick up this condition. Is P naught, maybe we call this as P initial, otherwise it's confusing. Whenever we see naught, we tend to think about 1 atm. Let's call this as P initial. It's 1 kPa. Let's try to do this. Try to calculate this. Then this T initial should be exactly as the T final, which is 100 degrees C. So now you see that since I need to specify both T initial and P initial, then I need to use super heated steam table. Okay. Why? Because I have to control both temperature and pressure. Otherwise, if you stick with the saturated steam, then of course you are able to only specify temperature or pressure, cannot control them simultaneously. This is why we need to use this superheated steam table. Right. So there I would have the value of H initial is kilojoule per kilogram. Have S initial, yes, okay. Then of course I could calculate my T initial is what? Is my H initial times minus T S initial. Okay, that T is 100 degrees C. Okay, this value is negative kilojoule per kilogram. From that, as we discussed in the partial molar Gibbs energy, which is mu initial, right? Then I have to compare the unit and figure out this is G initial times 18 kilojoule per kilomole, which is kilojoule per kilomole. Okay, finished calculating this mu initial. Then of course for the final state, of the saturated state, using the values for the vapor, and we can calculate G of the vapor is H of the vapor minus Ts of the vapor. So temperature here is still 100 degrees C. So there we could have kilojoule per kilogram. We convert that into mu of this vapor, is G of the vapor times okay. So now when you go back to the equation, now we have all the values we would need. So now if you revisit this equation, this is mu I interested in, this is mu I initial, is RT log Fi of my interest calculation. This is Fi initial. Okay. So now I have this value. I have calculated the initial. R is the gas constant, T is the temperature known, 100 degrees C. Now Fi initial is what? Is my P initial. Here's my 1 kPa. This is because I have this low pressure. Low pressure ideal gas, pure component vapor. Yi is 1. Right, so now you put all those values into this equation, then we figure out the fugacity of water at this 188, 100 degrees C. Yes. Right. Then of course the fugacity coefficient at that condition would be fugacity the one we just calculated over the whole system is 180. Okay, that would be this is the problem 1. Now if we move on to this problem 2, so the second example is not very nice, but I hope you can read this together with the lecture of 16. So the second example is this is example 2. That example is also a previous problem. This is problem 3 for final exam of 2017. Okay. So for this problem, I was asking the students to use the steam table and calculate the fugacity and fugacity coefficient for saturated steam at 150 degrees C. So now you see that the only difference is now we know T. Using the saturated steam, we are going to get the P, and then of course the value of H and S, and of course the G, of course the mu, right? There we are still going to set up the calculation as mu. Now this is the pure component, so I'm going to use mu as is. This is mu minus mu initial would be RTD log F, interesting, of F initial. Right, so I will do the same in order to figure out that the initial state is T is my known temperature, P initial is 1 kPa. Okay, and then of course this would be superheated. This is saturated. Okay, then you would have this H initial, S initial, you get this G initial, you get this mu initial. Alright, and then you finish your calculation.